And let's move on to the next presenter, Ander Ochoa from IBM Europe. He's going to be talking about deep learning for Cloud Pak for data. Ander Ochoa is a cognitive computing leader at IBM Europe and has been IBMer since 2000. Enjoyed most of the IBM departments, worked as infrastructure consultant in GBS, Linux developer in software, and power architecture pre-sales, and then power architect in IBM systems. He has worked with Linux almost since its inception, and he is a devoted open source believer. In the last 2 years, he has been bitten by the artificial intelligence fly, and now almost fully focused in IBM Power AI and all the AI ecosystem at IBM. Currently, he is a leader for Cognitive System Group with a group of fantastic professionals. With this, I'd like to invite Ander for his presentation. Ander, please go ahead and start your presentation.
Okay, thank you very much, Ganesan. Can you see the first slide of the presentation?
Yes, please go ahead.
Perfect. Okay. Well, as Ganesan said, my name is Ander Ochoa. I'm Cognitive Systems Architect for IBM SPIGI, meaning that I mainly work in the south of Europe, in Spain, Portugal, Greece, and Israel. And I have been working for IBM since 2000, a lot of years now. And well, my goal today is for those of you who may be working with Chineca's Marconi 100 supercomputer to allow you to get the most out of it, either if it's via the CLA or by using the state-of-the-art software that IBM has, that it's called today the IBM Cloud Pak for data. So in order to get this, I have prepared a small agenda. First of all, for those of you who don't know anything about IBM Power Servers, I will make a very brief introduction. For the rest of you, never mind. I promise it will be very fast. Then we will talk about the open power-based supercomputers that we have already started in other presentations. And obviously, we will talk about the building blocks of those supercomputers. Then we will go for the software side of this equation, because the hardware is very good, but also the software has to take advantage of all the good bits of the hardware. And then we will talk a bit about the state-of-the-art software solution that today IBM is putting into the market for artificial intelligence workloads. And we will run a demo of the Cloud Pak for data. So without further ado, let's go to introduce the open power architecture-based servers. Okay. Well, first of all, this is something I like to present to everyone, because everybody thinks that x86 is one architecture, that it's open. However, it's all the contrary. It's absolutely proprietary. Only Intel and AMD can build processors based in this architecture. And yes, those processors are very powerful, they are really good, but one day it may happen to them the same that happened to dinosaurs, that they may disappear. And things have started to happen because, for example, Apple has already ditched x86 processors and has started using another type of processors, the licensable architecture of ARM. ARM is one company that doesn't build anything. They just create designs, and then they sell those designs to anyone who wants to build processors, for example, for telephones, for tablets, for TVs, for computers as Apple, I don't know, for anyone, and they get money for this. Those companies that want to modify those designs to fit their needs better, they can do it, but they have to pay even more. And even on top of this, every time they sell one processor based in ARM architecture, they have to pay a small portion to ARM. So ARM-based processors can be really good. They are very, very good, but they can be quite expensive. So companies are starting to look at other places to build their processors. And we have the open architectures. There are several open architectures, but I think that the most important nowadays are RISC-V and OpenPower. RISC-V, it's a very new architecture. It's very young, but it has a huge momentum. But so far, it doesn't have very powerful examples of their processors. They are mainly in controllers and adapters, but one day they may become very relevant in the processor market. Meanwhile, we have the OpenPower architecture processors, and those are the ones that we have been talking today. The OpenPower processors are based in the power processors that IBM has built for a lot of years. IBM, well, first of all, they were developed as proprietary processors. Then IBM decided to change the license to licensable processors and created the OpenPower Foundation. And this foundation has worked quite well, but IBM then decided to open even more this OpenPower architecture and put it under the Linux Foundation umbrella. This means that if you want to build one OpenPower processor, you don't have to pay your royalties to anyone, if you don't want, of course. So as you can see, the same ones that manage the future of Linux may decide also the future of the OpenPower architecture. Obviously, IBM has a lot to say here. And speaking about the OpenPower Foundation, you can see how many companies we have there. And those are the companies that are pushing this architecture to new levels of performance. And you can see very well-known companies here, obviously as IBM, but also Infineon, Wistron, Tian, MSI, SanDisk, Xilinx, NVIDIA. There's a huge amount of them. Even Google is there. Actually, Google used to be the head of the OpenPower Foundation at the beginning. And this architecture, as the son of this architecture, it was developed in the POWER9 CPU. This is a power processor, very powerful, that we can proudly say that compared to equivalent x86 cores, it has twice the performance. It can have up to almost 3 times the memory per socket, and this is very important for some workloads. Also, and very important for what we will see later on, it has way more memory bandwidth per socket than x86 processors, and it can have up to 8 threads per core. Okay, I say up to 8 threads per core because sometimes we have, for example, 20 cores with 8 threads per core, or we can have 40 cores with 4 threads per core. Okay, it's more or less the same, but it's for different markets. Also, the servers that have been developed with POWER9 processors are really secure. Some of them are shipped with one hypervisor called PowerVM. This is not a software hypervisor, but like the rest of the market. It's more like a firmware hypervisor because it comes embedded into in the main server, and it is way more secure than the rest of the players in the market. We used to show one list from July 2013, where we showed like we haven't had any security breach in our whole lifetime, but this year I decided to check the US government database where those data are inserted, and I found that last year we found our first hypothetical security breach. Okay, however, if you see the rest of the players in this market, VMware, Shen, KVM, Hyper-V, well, they don't look very well in the photograph. So let's continue for the next one. This is the family of power servers that IBM has today. I will start from the right to the left. In the right side, we have the A980, which is the biggest server that we have today. It can have up to 192 cores and 64 terabytes of RAM, which is huge. It's a very powerful server. Then we have the scale-out servers, the ones with that start with 1S. They are way smaller. It's just 2U servers. They also have PowerVM, this hypervisor that we talked previously, and they can have up to 4 terabytes of RAM. And in the left, we have the newest additions to our line. The most important is the AC922, and it's the most important because it's the one that we are going to be talking today. Okay, so I will just go for the next slide. And this is the last slide of the introduction. I just wanted to show you that we have one architecture that it's really mature, it's really stable. It has been in the market for a lot of years. Actually, this slide shows Power4 that was sold for first time in 2001. But I have one poster at home that shows that Power1 was in the market in 1991. So it's now 30 years that we have been with this power architecture. Nowadays, we are working with Power9, but hopefully this year, in a couple of months or weeks, we will be able to start selling the Power10 processors with the Power10 servers, which will be very, very important also for the artificial intelligence market. So that's all about the introduction to Power servers. In case you don't know them and you want to know more about them, just let me know and I will try to explain more. So let's go for the open power based supercomputers. And this was introduced by James in the first presentation today, but it's really important because there is one list in internet called the top 500 list. It shows the most powerful supercomputers in the world, and it's really, really dynamic. And I want to emphasize this. It's very dynamic list. From 2018 to 2020, we have had the two most powerful supercomputers in the world. They are called Summit and Sierra. And they are based in the same components as the one you have here in Chineka, the Marconi 100. Okay. Just last year appeared a new supercomputer from Japan that took the position #1. And I think that the Marconi 100 now is not in position #9. I think I checked it last week and it was in position 11. As I said, this is a very, very dynamic list and it changes from one day to another. But still, it's very important to say that some of the most important supercomputers have been built by IBM. And as I said before, the most important thing is that they share exactly the same components. They have been built around the same building blocks. They share the same storage system, spectrum scale, or GPFS, as we used to call it. These GPFS systems or storage allows all the nodes to attack the same files at the same time. They are built also around the same network connectivity, meaning obviously they have Ethernet, but also they share Mellanox InfiniBand fabric to connect the nodes. And we will see how important this is for our workloads later on. Obviously, the computing nodes are based in Power9 servers, the AC922 servers, and they have between 2 and 6 NVIDIA GPUs, okay? Some supercomputers have 6 GPUs, but they have to be water-cooled, and some of them have 4 GPUs. The Marconi 100 that we have here in Chineka, it has 55 racks and it has 980 nodes, which is a lot of nodes, a lot of cores, and they also have the NVIDIA Volta V100. Well, you have here the specs of those servers. And I just wanted to repeat that those are exactly the same specs that the nodes that we have in the other supercomputers. So in order to be more powerful or less powerful, we only need to add more or less building blocks. Also, to show how powerful those nodes are, I want to show one that maybe some of you already know. It's one supercomputer that we have here in Spain. It's the Barcelona Supercomputing Center Mare Nostrum 4. It's the 4th version of the Mare Nostrum supercomputer, and in the 3rd version, it was built just around x86 servers. And in 30 racks, 30 without N, 30 racks, they had 1 petaflop of computing power. Well, for the Mare Nostrum 4, we added 3 racks, just 3 racks, and we added almost 1.5 petaflops of computing power. This is how different our supercomputers are to the x86 servers. Also, well, we have other supercomputers. For example, the most powerful private supercomputer in the world, that it was built for Total Fina, the French oil company, and it's based exactly in the same computing nodes for building blocks, for storage, for computing, for everything. And I just want to add the last one, which is the one for the MIT, which is called the Satori. Because, well, we, from our department in Spain, we helped John Kong, who is the leader for this supercomputer. We helped him to get this supercomputer, and we are really, really proud of it. And also, this Satori is the maintainer of the software that we will talk about later on. We have been talking about those computing nodes, and it's the AC922. Those are the computing nodes that you will find in all those supercomputers. They are exactly the same. The only difference is that, as I said before, they have 2 GPUs, 4 GPUs, or 6 GPUs. Okay. Usually, inside one supercomputer, you have only 6 GPUs, or you have only 4 GPUs. I have added here, for the geek inside of you, some diagrams of how those servers are and which are the components that they have, mainly because I guess that there is more people like me that I cannot get the most out of anything if I don't know what it has inside. So I wanted to show you how it is, how the guts of this server are. Also the front side, the rear side, well. I'm going to make a small stop here because I want to let you know that some of you may think, okay, the NVIDIA V100 is something that it's already old. Well, I reckon that it's maybe not the state of the art, but it's quite different to the NVIDIA V100 that we can find in x86 servers. As you can see, if we start from the upper side, it's based in the NVIDIA Volt architecture. It has 640 tensor cores. Those are the ones used to accelerate TensorFlow. Then we have the 5,000 CUDA cores. Then things start to diverge. We have slightly like 10% more double precision performance, slightly more single precision performance, and slightly more tensor performance. With the same capacity of GPU, with high memory bandwidth 2 memory, we have, this is the bandwidth between the processor of the GPU and the memory of the GPU. And here is where we can find the main difference. When the GPU is talking with the CPU of the system, in one x86 server, it has a bandwidth of 32 gigabytes per second. Meanwhile, when it's in our AC922 servers, it has 300 gigabytes per second bandwidth. And this makes a huge difference. It's a whole new world when we use this bandwidth compared to this one. Okay. Basically, this is the diagram of one AC922 server, which is the building block of those supercomputers and the one you have in Cineca. And you can see here 2 sockets. And we can see one red circle. Hopefully you will be able to see it around here, because I want to emphasize this thing. Both sockets are connected to one InfiniBand adapter. First of all, you should know that one adapter usually it's only linked to one socket, but this server has been design from the ground up, thinking in artificial intelligence workloads. So in order to do this, we linked this adapter to both sockets at the same time. Why? Because it will be used to exchange data from the memory to the memory of another nodes. And to be able to do it with the lowest latency possible, it's connected to both sockets at the same time. Okay, so we can take data from both NUMA nodes to another NUMA nodes of another computing nodes. Also, there is another green circle here that it's covering the connection between the GPUs, which are those ones, and the CPUs. The GPUs connect using one bus called NVLink, which runs at 150 gigabytes per second. And in one x86 server, they would connect to the main processor using PCI Express version 3, which is 16 gigabytes per second. However, we use also NVLink because we have one NVLink small portion in the POWER9 processor. So it can talk NVLink with the NVIDIA GPUs. And why? Because this way, the NVIDIA GPU can access the data in the main memory at the fastest possible speed. So we will be able to feed the GPU with data from the main memory. And you will see how we will be able to do something really, really beautiful with the software. So without further ado, let's talk about the software. And here I'm going to talk just about three things, okay? Large memory support, distributed deep learning, and other frameworks, well, one framework, just one, called SnapML. The LMS, and forget what you can see here in the slide. When you are running one training in one server, you have to use the memory of the GPU. And the GPU could be 16 gigs, 52 gigs, 48, even 80 gigs, but it's limited. And this is very good for structured data. But when we are using unstructured data, meaning images, this can be a problem. Why? Because usually the more resolution that those images have, the better our trainings will be, the better our models will be. So by using LMS, we will be able to use up to 2 terabytes of data for our trainings in the GPUs, instead of being restricted to using just 16 or 32 or whatever the number of memory that those adapters have. And this is really good because if you compare it between x86 V100 GPUs against Power-based V100 GPUs, we can make some trainings up to 4 times faster. But as I said, this is good, but it's not something that makes the difference. What makes the difference is this. We can use images that weight way more, and they weight way more because they have more resolution. Depending on which is the network that we use, we can have up to 10 times more resolution images. And this is something that at least it's a tautology that in artificial intelligence, the more resolution you have, the better your training will be. At least is what I have seen so far. I'm not going to explain more about LMS. I will leave you here some examples of how to use it, for example, in Café, how to use it in, well, this is one example that we run in the Barcelona Supercomputing Center, and I will leave you there. It's proved, it works, and it's quite interesting for those of you who may need to run it. Also, some information of how to instantiate it or how to run it from Keras or Estimator APIs, and some more information. I don't want to go deeper because we don't have enough time. We could be talking about this a lot. The second thing I wanted to talk about, it's the distributed deep learning. What's this? This is what we call the DDL, and it's basically, for those of you who may know about it, it's the same as Horobot. At the beginning of the artificial intelligence, whenever you wanted to run a training, you had to use just the resources that you have inside one computer. If you have 2 GPUs, you can use 1 GPU or 2 GPUs, but you cannot use more GPUs for your training. However, by using DDL, you can bypass the boundaries of your server and use the resources of another that you can find in another nodes. For example, you can use the GPUs in another nodes for your training. And by making this, you can reduce the training times, for example, for 16 days to 7 hours, just increasing the number of nodes. This is one very beautiful example because it shows how going from 4 GPUs in one node to 256 GPUs in 64 nodes, we can achieve 59% of efficiency. And this is huge, also because it was achieved with the previous version of the AC92, what we used to call the Minsky servers. I will leave you here the code that we ran in the Barcelona Supercomputing Center some time ago. And this is how we run the DDL workloads, okay? Also, well, this one was using Slurm. I don't know if you use Slurm in Cineca, in the Marconi 100, but you have the example with Slurm and without it. Last thing that I wanted to show you, it's one framework that has created IBM research. Usually when we are talking about deep learning, we are talking just about those two ways of attacking the problems. However, we have a huge amount of way more used ways of attacking the problems. For example, logistic regressions, decision trees, random forests, whatever. And those are usually always run in the CPUs. So in order to change this, IBM Research created the SnapML. This is a framework that is API equivalent to Scikit. So you can instantiate it and you don't have to change anything else. And it's applicable to logistic regressions, linear regressions, ridge, well, all those things. And you can get up to 4 times faster trainings by using those this framework. All those 3 components, you can find it in something that it's always shipped with the AC92 servers, and it's free to download from the internet, something called the Watson Machine Learning Community Edition. However, lately we have seen that, well, it's quite difficult to keep the same pace with the community because it's very, very dynamic and they request new versions of everything. And IBM has decided to give this set of tools to the community, and they are called now OpenCE. Now they lack some of the bits that we have talked before, but you can select in those servers, you can select to run either of them. You can find more information about this in one web page of Meet Satori, and I will leave you here the link so you can check there which one you want to use for your workloads. As I said, in the OpenCE, you will find the most advanced and the newest versions of almost everything that we usually use. And this is about what we usually do with CLI. However, IBM nowadays, as everybody knows, acquired Red Hat, and Red Hat has a very, very interesting thing called Red Hat OpenShift, which is like one, we could call it one hypervisor for containers. So IBM has decided to put all the software that usually was in the market separated. IBM has decided to put it in different sets. Each of those sets is called a Cloud Pack, and the Cloud Pack for artificial intelligence workloads is called Cloud Pack for data. It has a huge amount of components inside. I'm not going to list all of them. It's a huge amount of them. Also, I'm going to say that it can take data from almost anything in the world, from Hadoop, DB2, Cognos, whatever. It can take data from everywhere. And most interestingly, it can handle one artificial intelligence workload for its whole life cycle. So we can start from when the data is in one data lake, transformation, creation of the training, and then putting it into production in the same place with the same hardware. And actually, this is what we are going to try to run today in our demo. And here comes the demo of this Cloud Pack for Data. Just 2 slides before showing you which is the hardware where we are going to run it. It's one Power IC922 server. It's quite similar to the AC922. However, this one has no GPUs. Sorry, we ran out of money when we ordered this, and so we couldn't add any GPU to this one. It has 40 cores with SMT4, so it's 160 threads. It has 2 terabytes of memory, but we will be using just one, and it's running Red Hat 8 in it. Also, it has, I think it's 8 SSDs of 1 terabyte each one. So we installed this server, we installed Red Hat 8.3, I think it's running today. And over it, we installed the Red Hat OpenShift. As this server comes also without PowerVM, the firmware hypervisor, we used the regular Linux hypervisor, the KVM, and we created 9 virtual machines. 3 virtual machines are for the master nodes, and this is a requirement from Red Hat. We cannot change it. And we created 6 worker nodes. As we had so many resources, we decided to create 6. I think the minimum is 2, but for Cloud Pack for Data, the minimum should be 4. But we decided to go for 6. By the way, I will leave you here the link that it's a public link, and it shows perfectly well how to install Cloud Pack for Data in your Red Hat OpenShift. So you can follow it and you can ask me if you want, but it's quite simple. Once you have done it once, it's very fast to run it. So I'm going to try to change the screen to my, here. This one. Sorry, just 1 second. I have to find where. Let's see. Aha, here it is. So, Firefox. So, can you see Firefox now? Okay, now you should be watching Firefox. And this is the login page of the Red Hat OpenShift. We run it with kubeadmin and a very strange password. And this is the main dashboard for Red Hat OpenShift, okay? It has several things. It shows the version. We're in the state-of-the-art version for branch 4.6. Well, it shows some resources like the CPU. As I said, we have 160 threads, so we are using just 7 threads. Right now, we are using 100 gigs out of 800 that we have available, the file system, network transfer, some very nice data from it. Also, we can see the 9 nodes that we have created, the 3 master nodes, and the 6 worker nodes that we have. And we can see here how many pods they are running. You can see the pods as if it was container. It's not exactly the same, but we can think that they are like the containers that they are running right now. Also memory, CPU, and so on. As I said, I followed this public available information to install Cloud Pack for Data once I had the Red Hat OpenShift. And let's go for the Cloud Pack for Data. It's also something that we have to reach using one web browser. And here we put the administrator password and the very strange password, and we can log in. So we can see here the main dashboard for Cloud Pack for Data. Here we can make several things. We are going to focus in running our project. And the project I have selected here is one diabetes prediction project. We're going to try to predict if someone is going to develop diabetes during their lifetime. In order to do this, I have added a small CSV file and you can look at it as if it was one Excel file. It has almost 800 rows and it has 9 columns. Those are what we call in artificial intelligence the features, and those features shows us well, I have to say that this is one Excel file that I downloaded from Kaggle, and it shows data from one original community in North America from women. And those columns show, for example, if they have been pregnant or not, and how many pregnancies they have had, glucose levels, blood pressure levels, well, and some more relevant data that probably, if any one of you is in the healthcare business, will understand better than I do. But the most important thing is the last column, and this is the outcome. This shows if this person has developed diabetes during their lifetime. It shows you with 1 if they have developed diabetes and 0 if they haven't. Here we could take this data and refine it. We can change it in the way we want. Okay. Here we can see the first 50 rows and we can change it. We can do whatever we need with them. I'm not going to change anything right now. And now that we know the data set that we are going to use for this demo, we are going to create something called one auto AI experiment. And what's this? Well, let me show you. For this auto AI experiment, I'm going to call it Chimeca 1, for example. Oh, it allows us to select the number of resources, sorry, but as it is such a small data set, it makes no difference selecting more resources or less resources. It takes exactly the same time. So now that we have created the auto AI experiment, we will let it know which is the data set that we are going to use. And here you can see that we have selected the same data set. And now we start watching some interesting things, like those graphics that represent the values that we can see in the columns. And here at the end, the outcome, which means 0 if they haven't developed diabetes and 1 if they have developed diabetes. So let's close this window. And now it asks us to tell it which is what we want to predict. And what we want to predict is the outcome. So we just run the experiment. As you can see, you don't need to be one super duper data scientist to run this thing. Of course, the more you know, the more you can get out of this tool. But so far, I'm not one data scientist, and I have been able at least to run it. Probably you can see here some moving dots. Right now, it's taken all the data, the 800 rows, and it's dividing it in 2 parts. 90% of it is going to be used for the training, and 10% of it is going to be used to test. So let's see. Well, meanwhile, I will show you that also here we can select how we want to rank it. It has to start first. Sorry for this. Let's see. Well, usually this test takes only 4 minutes, between 3 and 4 minutes. Probably in this demo it will take more, just to show me wrong, but it should take just 4 minutes. As I said, it has taken 90% of the data for training and 10% for tests. And right now, it's creating different pipelines. Each pipeline is one approach of getting the best accuracy. I say, for example, accuracy, but we can rank it selecting accuracy, average precision, balanced accuracy, F1, log loss, whatever we want, okay? And each of those pipelines, as you can see here, This is the first pipeline, second, third one is the one it's using right now, or is creating. It uses one start to show us the best one, at least ranked by what we have selected here. And while it's doing it, we can select whatever we want, the first pipeline, and it will show us very interesting data. For example, the accuracy of this one, the precision, recall, F1, log loss, whatever. Also very interesting, confusion matrix, and several more data for this model that it has achieved this accuracy. I'm going to close this one just to let you see. It will create 9 pipelines, and we will be able to select the best one. I don't know, for example, in accuracy, but we could select average precision, whatever. It's already finishing. As I said, it will take just 4 minutes, but we can see some interesting stuff like pipeline comparison here under all those values that we have selected. And after this, we will be able to take the winning pipeline that we want, or that we prefer, oops, sorry, and we can save it. And we can save it in 2 different ways. They are very interesting. As a notebook, as you can see here, we can create a notebook with it. It should be quite fast. Yes, it is. And it creates a notebook with this pipeline and the model it has created. This is very, very interesting for administrative purposes. And also, of course, it will allow us to edit it and run it as one typical Jupyter notebook. I mean, we could use a typical Jupyter notebook, but this is exactly the same. You can run step by step, modify it, whatever. So I will go back to my projects. Oh, come on. So let me go back to our Auto AI experiment. So here is the notebook we just created, but we will go here to our Auto AI experiment that should be almost over in just some seconds. Well, anyway, probably this will be the winning pipeline. So we are going to save it, not as a notebook, but as a model. As some of you have already understood, what this creates is different models, each one with the right rank. And with these models, we can save them and we can promote them to deployment space. I'm going to promote this to our deployment space. We call it serial space. No tags, just promote it, okay? Okay, so now it's promoted and we can find it here in our serial space. And this model that have been promoted to our serial space can be deployed. And it can be deployed in 2 different ways. In batch mode, and this is very interesting, if we create a model that we want to run at one particular hour, for example, during the night, because we know that there will be more available resources during the night, we can run it as batch model, or we can run it as one online model. And we will focus here in the online model. It's more interactive. So we will call it Chimeca one online model. Create. Okay, so right now, here you can see it's in progress. It takes like 2 or 3 minutes. However, it will be exactly the same as this one that I have already created, just in case something went wrong, but everything has gone very well. So this is diabetes prediction model online. So the tool will show us the necessary code to instantiate this model, to call this model by using curl, Java. Java, we need more code. With JavaScript, with Python, with Scala, and it will be calling one URL. So it can be run from whatever part of the world we want that has access to this URL. And one test of it, we are going to run it. Here, for example, we are going to say, one person that has had 2 pregnancies during their lifetime with a glucose level of 120, for example, I have no clue if those values are good or not. So probably I'm going to kill this person, but we will run the test. A blood pressure of 23, skin thickness of 43, insulin of 100, body mass index of 21, diabetes pedigree function, no idea what it is, 1, and age 21. So we run prediction, and this is what the call would get. It gets a 0 because it's not going to develop diabetes, and it has a probability of 94%. So it's quite good. Obviously, don't think those figures are completely meaningless. It's just one example, and it just wanted to show you how easy it is to start one project from the start to the finish. And also, I want to remark very clearly that this is not a magic wand that it's going to run all your artificial intelligence workloads in 3 minutes, as we did here today. No, this is a tool to help you kickstart your artificial intelligence project. When we start one artificial intelligence project, the data scientists gather together and start thinking, okay, we should take this approach or the other one or the other one. Well, it may take for them days or weeks to decide which is the better approach. With this tool, we are going to be able to kickstart in the right direction, or probably in the right direction, our artificial intelligence workload, and it will give us one advantage against those ones who don't use it. And I think that's all I have for today. So I will give control to Ganesan, and thank you very much for being with us today.
Sure. And thank you very much for the wonderful presentation, and also you took us, nearly 45 minutes of, the Cloud Pak for data and the various, the open power systems in the top 500, and also the Sinica system and everything. Thank you very much for the presentation. And any questions for Ander from audience and panelists? Any questions? Okay, let's move on. I know that it's almost 4 hours since we started this workshop, and really a technology feast. Lots of content we had, starting from power, the open power foundation capabilities, the power innovation, and open CAPI, LibreSoc, their own core, the power core using the Power ISA, and the BOA, the Bayesian optimization accelerator, and the Cloud Pak for data with a lot of other features. It's a kind of a technology stack containing from the silicon to the solution. That's how I wanted to have this kind of workshop so that people can get an understanding about the entire computer stack from the architecture to the application. Like any way you put it, this is how people want us to learn about accelerator, the CPU, the FPGA, and the GPU processing, and developing your own the processor core and applications, and the computational fluid dynamics and all the stuff.